Okay, so this lab was talking about the oscillation of a mass on a spring. Kinetic, gravitational, and spring energy are three fundamental forms of energy in physics, each representing different aspects of motion, position in a gravitational field, and potential energy stored in a deformed object. The purpose of this lab was to analyze the motion of a mass oscillating vertically on a spring. We compared the observed motion of the mass in the x and y directions with the predicted motion using a computational model. We also measured the change in kinetic, gravitational potential, and spring potential energy of the spring mass system to apply the energy principle. So, some fundamental principles and concepts that we applied. First, Newton's second law, which includes the velocity update formula and the position update formula. The energy principle, which says that the total change in energy of the system is zero if the work done by the surroundings and the change in thermal energy is zero. And we identified three different types of energies, which were kinetic energy, gravitational potential energy, and spring potential energy. And kinetic energy is equal to 1 half mv squared, gravitational potential is equal to mgy, and spring potential is equal to 1 half ks squared. So some assumptions that I made in the system. First is that the system is frictionless, the spring obeys Hooke's law, and that energy is conserved throughout the system. So delta E system equals zero. And a preview is that the predicted and observed motion of mass are similar in both the x and y directions, and the total change in energy is zero as reflected by the changes in other energies. So this is how I analyze my observed motion in trackers. So I set my system to be the mass, the spring, and the earth. So the surroundings is nothing. So the work done by the surroundings is zero. The object mass was 0.402 kilograms. The initial position of the mass in my coordinate system was 0 - 0.8390 meters, and the initial velocity was zero. The spring coefficient was 6.83, and the relaxed length of the spring was 0.123 meters. And then I set my starting frame to be the seventh frame, and the time between each image was 10.5 seconds. So the way I predicted the motion using a computational model. So first you define your initial conditions and constants, then you calculate all the forces and apply the momentum principle. So the force of gravity, the spring force, and then calculate the net force, and then you update the velocity and the position based on the net force, and then also update the spring length and S. And then from there you can calculate the energy changes, which K, delta K, the gravitational potential energy, change in gravitational potential, the spring potential, and then the change in the spring potential. And then from there you can calculate the total energy and set the total change in energy to be zero. So the results were that the observed and predicted positions in both the x and y directions were very similar between the observed and the predicted model, as shown here on the graphs. I would say that the observed and predicted positions for the x direction were a bit more similar than in the y direction, but overall, it was a really accurate prediction. And then for the energy graph, here you can see that the change in gravitational potential energy and the spring potential energy are opposite in sign and oscillate. And the change in kinetic energy is less in magnitude, but also oscillates. And the change in total energy is always zero, as shown here by the horizontal line. And some potential sources of error could be that the drag force was not accounted for, thermal energy and rotational kinetic energy were not accounted for, and it could have been an inconsistent center of mass when I was plotting the mass in Tracker. What does this mean? So the energy principle was satisfied because the total energy was zero, which is shown on the graph here by this horizontal line. Therefore, the change in energy of the system is zero, so the energy principle is conserved. For the oscillation period, I was able to calculate the oscillation period for both the x and y positions just by looking at the data for the positions. So the oscillation period for the x direction was 1.23 seconds. For the y direction was roughly 1.14 seconds with a difference of 0.09 seconds. And this difference affects the calculation of the spring constant K, which affects the spring force and the spring potential energy. And why is this even a difference? It could be because of the drag force or air resistance acting in the y direction, and again, differences with tracking my center of mass. Thank you.